Hello and welcome to another one of D's ADD videos. Today we're going to be looking at the concept of heating and cooling curves. What are heating and cooling curves? Well, they basically are curves in which the y-axis will be temperature and the x-axis is time. And we always look at 1 mole of the substance and we can calculate the heat either emitted in a cooling curve or absorbed in a heating curve. So in a heating curve, for instance, as time passes, we add heat to the system and look at the temperature. In a cooling curve, heat is removed as time passes and we look at the temperature. All of these slanted portions have just one phase. First phase, or the bottommost phase, will be solid, whether heat or cooling curve. The middle one will always be just pure liquid, and the top one would be just gas or vapor. So now at this point, when we look at the flat portions, we have a transition occurring. For instance, here we're going from a solid to a liquid. And you notice how it's a flat portion. That means it's the same temperature. Okay? And what's happening is the ice, if we're dealing with water, is melting into liquid. Okay? We will refer to this process as fusion, not melting. So if you see fusion, it's the same thing as melting. And then we have pure liquid, and temperature occurs, or temperature change occurs as more heat is added. And if it was water at 100 degrees Celsius, our boiling point, we would start getting some of the liquid turning into gas, right? Not all of it occurs simultaneously, so it takes a little bit of time, more heat is added. And then once we have converted all of the liquid into vapor, then we're in the vapor phase, which is slanted. So it's liquid and gas or vapor here. And a cooling curve works much in the same way, except for it's in the opposite direction. So we condense to form liquid from a vapor phase or gas phase, and we end up with liquid, and then at the freezing point, we end up with a combination of solid and liquid until we've converted all of it to solid. If we're dealing with water, again, it would be ice. And then it would be all solid. All right? So, because these regions here have a change of temperature, there's a specific enthalpy formula that you must use. Whereas the flat regions don't change in temperature, and there's a different formula. So let's check out the two different formulas. So for the slanted regions, because there's a change in temperature, we use the heat capacity formula, or the specific heat if you're given mass times change in temperature. Okay? That's for the slanted portions. And that's because there's temperature changes. That makes sense. Now for the flat portion, I can't really use this formula because delta T would be 0, and we'd always get 0 enthalpies there. So we have to use a different formula. So this is just showing again that the flat portions are a combination of both solid and liquid, or liquid and gas. You'll see that here. Oops, sorry about that. You'll see that here with the abbreviations that I've made. So here, it doesn't make sense, like I said, to use the same formulas for Q, so we use a delta H times moles, where N is a number of moles. And delta H is going to be the enthalpy associated with a given process. So, for instance, if we're looking at a heating curve, and we're going from solid to liquid, so we're looking at this flat portion right here, whenever we're doing that, we have to use the one for fusion. And let's say we're dealing with water, and here's a handy dandy table. This information should be given to you. You should know that fusion also means melting. Vaporization is liquid to steam or vapor or gas. sublimation is from solid to vapor. And for water, these are the different enthalpies associated with 1 mole. Okay? And if we're looking for the reverse of the process, let's say we're doing a cooling curve, then you just take the negative of these values because it's just the reverse of the process there. Okay? So if I'm going from, my ankle just popped. If I'm going from liquid to, or from gas to liquid, if I'm condensing, it'd be a negative 40.67. All right. So that's the basics of a heating and cooling curve. I'll go through an example of both a heating and cooling curve and calculate the enthalpies of a transition. We'll do one easy one that's just here in this region or just in this region. But then we'll go, more likely what you'll get is they'll want to know what the enthalpy is from going from a piece of ice at negative 8 degrees Celsius all the way up to vapor at 110 degrees Celsius. Well, you can see that involves 1, 2, 3 slanted regions and 2 flat regions. So you would have to do 5 total formulas there and add up all the enthalpies. All right, so it can get complex, but if you start now and practice enough, all this stuff can break down to very workable, understandable steps, okay? You just have to practice it. Hope I've clarified any confusion you might have, enough for you to practice. Thank you and have a nice day.